People can know they should leave.
Why? Because they're not hot. They'll stay there.
Well, that's a bad way to do it. It's on fire. It's not hot, I'm fine.
It would be.
Anyway, you guys clearly know more about it than I do. I'll ask the question during live. Maybe we can get a. This building's not as bad as Salem. Modern buildings have a lot of chemicals in them, like in the building materials. You should not, like, you wouldn't want to just stand like right outside. But they're drills, right? Like, yeah, I'm recording this. I should say this. I've always thought fire drills are stupid. Well, like, you should absolutely know where your exit is, and you should know what the fire alarm sounds like. But if you know those two things, like, it's not like it changes. It's not like this time we're gonna like run some pattern as we like. When the alarm goes off, you leave as quickly as possible, and yeah, you should get as far away from the building as possible. Right, and that's my problem with a fire drill is you should never wonder. Like, if you hear the fire alarm, you should leave. Because I did this once in Salem, maybe, I don't know, 2008, 2009. I was in my office working, and I just wanted to finish. I heard, like, we had the same kind of old building sharing, and the fire alarm would go off a lot. And it went off one day, and I'm like, this just pisses me off. And I'm gonna finish what I'm doing. And I'm like, I'm going home. I'm just gonna. So I packed my bag up. You know, I'm just like, I opened the door. Old Salem, you don't know it, but my office was inside my lab. So I opened the door, and smoke is about to heat. Like, the smoke is from the ceiling down to about here. I opened the door and smoke, and I'm like, I'm gonna die because I wanted to finish my email. I'm gonna die. I'm gonna burn to death because I wanted to finish an email. Like, I am an idiot. like that's my one goal for dying now. Like, you know, I'm 51. I'm almost certainly past halfway. Right? Like, best case, I just don't want to feel really stupid before I die. Right? I don't want to see it coming and be like, I could have avoided this had I just been a little smarter. That's my goal. So, all right. Now that I've talked about death and fire, we're gonna do. So we got class today. We got class on Monday, and then we don't have class a week from today. I assume you all know that. You guys are usually pretty good about figuring out when we don't have class. So I'm going to do one last way to make a mean. This one is a little tricky, but we've seen it. So, and this is also an SN2, but this is a really good way of making a primary mean. We can use a nitrile. So this is not going to simply replace a leaving group with a nitrogen. It's going to add a carbon. Right? So SN2. I saw this in my notes last night, or as I was thinking about class, and realized I didn't get this on the board last time. So now, like, we go from 4 carbons to 5 carbons. We have this nitrogen. You can reduce this with lithium aluminum hydride, and you can just reduce it straight down. So we talked about reductive amination, reducing a carbon nitrogen double bond to an amine. Well, this is reducing a carbon nitrogen triple bond. And so And again, all these synthesis of amines require us to get the nitrogen into the molecule in such a way that it's not immediately nucleophilic, right? If you think back to my discussion of all that, I don't know if you got the upshot of that is if you just use ammonia or an amine, you try to alkylate it, the tendency is to over-alkylate. That nitrogen, the amine ends up basic and nucleophilic and it just keeps going. So all of these are ways of, like with nitrile, we put the nitrogen in as a triple bond. That nitrogen's not nucleophilic, but it's not very nucleophilic. And so then we can sort of stop the reaction. We get the alkyl bromide away from it. We reduce it. We get a primary amine that's stuck. Right. So then if we wanted to do this and get 4 carbons, right, the anion we would use would be very good. The anion we would use would be azide. This is reviewed from last time. And then I talked about a variety of ways of reducing that. So with cyanide, we add a carbon. With azide, we have the same number of carbons as we started with. Okay, so the next thing to talk about, that sort of was an addendum to Monday's class. This next one is a neat reaction that you guys have done. So this is called diazidization. So if you take an amine and you treat it with sodium nitrite, N-I-T-R-I-T-E, and HCl, you end up with basically adding this nitrogen as a triple bond to the amino nitrogen. There's a lot of cool chemistry in this. Dr. Bruce King in the department has studied a lot of these small molecules. So when I was your age, we just thought these oxides of nitrogen were pollutants. So along with, you've probably read about acid rain, along with that. So back in the mid 20th century, right, we sort of look at this technology. We can cool our rooms. We can cross the continent in a couple of days. It was magical time. We had very dirty fuel, and that out of the exhaust, you get these oxidized nitrogen compounds and sulfur compounds, and those would interact with molecules in the air to really dirty the air. Like the air was, so right today, the issue is carbon dioxide, global warming, that sort of thing. You can't really see carbon dioxide. If you look out tonight, clearish day, if we, raise the amount of CO2 in the air by 1,000 times, which would, either short or long term kill us all, you wouldn't be able to see it. CO2 is a colorless gas. You would see it. If you even increase the nitrogen oxides and the sulfur oxides by a factor of 2 or 3, we would see it. The air would get brown. You'd notice it when you go outside, you'd breathe, it would hurt to breathe. And you can find examples of this still on the planet. But most of the world, we cleaned up the, it was good. We cleaned up the air. The bad part of that is it becomes hard to convince people when there's a problem, right? Like the air's fine to breathe. It looks good. Like we're all fine. Anyway, it turns out that those same molecules, so nitric oxide, NO, which is toxic at higher doses, turns out to actually be a transmitter in biological systems. So these little molecules, nature has figured out a way to use them, dissolved, to float around. So we're sort of using that here. this reaction, so you guys actually did this reaction as the first step of making an azo dye. I'm not going to require you guys to know this mechanism, but if you draw the Lewis structure out of NO2 minus, you get this. Right, so if we protonate that, you get this, and it's soluble in water. It also is a gas. I just like the name. I don't know, like it's actually, that's the molecular formula. It's the name of it. And then the mechanism's it's actually a fairly complex mechanism as to how this happens. But if we protonate this again, actually, let's do that. Where would you put that proton? Three spots you might put the proton. Yeah, well, it's not a carbonyl, it's a nitrogen, right? But like there's what you're saying. Yeah. So it's an NO double bond. That looks like it does behave in many ways similarly to a carbonyl CO double bond. And in fact, that's where I would put the proton as well. So you would end up with this. Right? And then you can have a resonance structure like that. The other plausible place to put the proton would be on the nitrogen. That doesn't then have any resonance structures, but it's a nitrogen with a lone pair of electrons. Like it's bonded to two electronegative atoms, so it's not very basic, but you can put it there. Where you really can't put it is here. And yet this is the one, I think it probably is in your book that's where you go. So this is then going to lose, this protonated species is going to lose water. And we're going to end up with these two things. We'll lose water out of that. I know a lot of undergraduate textbooks say to put the proton here and then use a lone pair on the oxygen, push out water. But that is not, that species doesn't get formed, which is a big reason I'm not going to ask you guys to work with this mechanism. This is very similar to the nitration mechanism. If you go back to like the beginning of the semester, when it was hot in here, maybe you thought the building was on fire, 100 degrees outside. When you make NO2 plus, an electrophilic aromatic substitution, so you mix nitric acid and sulfuric acid. The nitric acid is protonated; it loses water to give NO2 plus. Here we have one fewer oxygen at the beginning. So if you see this, you can assume that it makes this NO plus. So nitric oxide, the thing I said, is a transmitter in your, call them cathode transmitters. So basically, there are all these transmitting molecules that sort of take messages from one place in an organism to another place. Nitric oxide is one of those. Nitric oxide is NO plus minus an electron. So I'm knocking one electron out of here. Nitroxyl is another one. So it's NO minus, usually bonded to a hydrogen. You don't get a lot of NO plus in your body. And the reason is, right, that NO plus is quite electrophilic. And so let's take a secondary. If you take a secondary amine and treat this with NO plus, this out. You wind up with an N-nitroso compound. If you guys end up studying molecular biology or cancer biology, N-nitroso compounds are carcinogenic. They're not naturally formed, so if you wind up with those, In your cells, you can get problems from this. Nitrite, so you'll also sometimes read about people being allergic or sensitive to nitrites. And this is largely what they're being sensitive to. So I'm not gonna, like I said, we're not gonna go much farther with this. But I am gonna go through how, well, I don't even think I'm gonna go through that whole mechanism. You get N-nitroso compounds with secondary amine, right? So this nitrogen's got two things on it. If you start with primary amine, we get to the same place, right? We make an N-nitroso compound, but now there are hydrogens to lose, and we're going to lose those. The first one just comes off. Okay, so just lose one of those. Get that neutral. So once you get to the N-nitroso compound, but you still have a hydrogen on that nitrogen, on the nucleophilic nitrogen, you can do a keto-enol tautomerization. I'm managing my board badly. Take it rid of the blue one here. So we're going to do a solvent-assisted proton transfer. So draw a resonance structure for what I just did. Resonance, these are great for practicing your resonance structure. So for this molecule right here, draw a resonance structure of that thing. That's more stable, I should say that. There's lots of resonance structures you could draw. So remember, in a resonance structure, your total charge is going to be the same. So if I ask you to draw a resonance structure of something's got a minus and a plus, you can draw a completely neutral resonance structure. And what you end up with is that, right? So basically, just have that N minus make a double bond, and then neutralize the positive charge on the trivalent oxygen. This, that. So then again, we're going to protonate. So now we are going to protonate this oxygen. So what do we need to do? So once we protonate this OH, how do we get to the diazo cation I've drawn up above? You can just draw it on in your notes if you want.
remember, both of these nitrogens have lone pairs on them. Actually, a lone pair up here too. So we can just take lone pair on that one, make the triple bond, push that out, lose water. We get an aryl diazonium salt. So I should write the name of this. All right, like I said, you guys made this in lab a couple of weeks ago. A couple of weeks, was it, or was it last week? Was the azo dye last week? Reductive, what was it last week? Azo dye. Okay. About half of you were shaking your heads. To me to remember. All right, so you made this in the first half of the azo dye lab. We'll talk about the second bit of that. There's going to be a bit of an interruption, and then we'll come back and talk about the second. So this whole mechanism is, you know, it looks long, but it's just moving electrons around. Same thing you guys have seen forever. Nucleophilic atom attacks an electrophilic atom. Acid base, proton transfer, protonate, proton. So that's a proton transfer. Sorry, here. Lose water, elimination. Again, like I talked about going into exam 2, you guys, if you try to memorize every entire mechanism, you're gonna exhaust your brain power, right? So if they're all modular, nucleophilic attack, proton transfer, elimination, you know, just kind of string them together and always have an eye on where you're trying to go. All right, you can do this exact same chemistry with any primary amine, and you'll end up with a diazo something. So this is diazomethane. Diazomethane is hard to work with. The aryl diazonium salt, I don't know if you guys remember, right? You made this, you took your aniline compound, you added sodium nitrite and HCl. It was in your beaker, you kept it at 0 degrees, but you didn't really do anything special with it. We let you do it. We made you wear safety glasses, that was it. Diazomethane, alkyl diazo compounds tend to explode. All right, this whole chapter is fun for explosion. If you like exploding things, this whole chapter pretty much does that. Again, remember what I said about what an explosive has to do. An explosive has to exothermically liberate gas. So the gas that comes off of diazomethane is N2 gas. Right? And you're breaking, and N2 is really stable. So if we can bond something else here and kick out N2, right? N2 is going to be a fantastic leaving group. Think back to Orgo 1, water is a good leaving group because it's a nice stable molecule. Well, N2 is way more stable than water. So N2 is a great leaving group. Why then is this compound, why is the aryl diazonium salt more stable than conjugate? It's conjugated, right? We've got the N2 pi bonds conjugated to the benzene. And again, you have to keep that aryl diazonium at 0 degrees. As I went around the lab, some people didn't get a whole lot of solid. There could be a lot of reasons for that. You definitely have to get the pH right. And, I know a couple of groups didn't, if they added a little more HCl, they got more precipitate. But one reason is this will decompose, right? It's not, again, N2 can leave that really nicely, but it's more stable, so N2 doesn't leave as fast. It's not as exothermic when it does. Aryl diazonium salts tend not to explode. This is why I don't really teach this before we do it, because they tend not to explode. You can make them explode, and I never want you guys to try. That's always my word. All right. So the technical. There you go. All right. So that from that aryl diazonium salt. We get some chemistry called Stanmeyer chemistry. Name for the guy who did it. Let me come back. This reaction right here, you need to know. Right? You need to know that if you take sodium nitrite and HCl or HONO and you treat an aniline, that you're going to get an aryl diazonium salt. And then there's a lot of cool chemistry you can do here. So if you treat an aryl diazonium salt with copper chloride, the chloride displaces the N2.
Still on the screen. I'm not still on the screen.
You do this with copper bromide. What are you going to get if we use copper bromide? Pattern recognition, right? What do we think? Yeah, copper iodide. The other thing we can do, and I didn't write the stupid reagent down, did I?
I did not.
So you guys know reactions that will put a chlorine, bromine, and iodine on a benzene already. So that's maybe not super useful. If you think back to electrophilic aromatic substitution though, right, if I have other substituents on here, they may direct to the wrong place. They may direct to two places. And so I'm going to get chlorine in two different places. I might get chlorine only in the wrong place, the place I don't want it. Here, the carbon that's got the N2 is the carbon that gets the halide. So I have specificity of that reaction. I can also put a fluorine on, which I can't do. And look this up. It's not, I think it's a, there's an antimony F6. I didn't write the reagent down because when I was writing the notes out, I'm like, I know this reagent. And I don't remember the reagent. So it's in the textbook. The other cool, is it just SPF6? Oh, you're right. You're saying what I. The other nice, this is a really neat reaction. H3PO2 hypophosphorous acid replaces the N2 with an H. Right, so if you have an NH2 on your ring and you need to get rid of it, you can diazetize it, treat it with hypophosphorous acid, and then it's gone. Treat this with peroxide and OH, and you can replace the N2 with OH. You can also sometimes just do this with water. This one is one that this is sort of what the aryl diazonium salt, if you just put it in water, which it's in when you make it, and just let it decompose, this is usually what it decomposes to. Heating it up can be, again, you always want to be as gentle with reactions as you can. You don't want to, right, you don't want to heat it hotter than it needs to go. So we do that in a teaching lab where we have a 4-hour slot, right? We have to complete the whole thing in 4 hours. And we usually like to do it in 2:10 if we can. In research lab, if I want a high yield and not have to worry about purifying it away from a whole bunch of crap, I will let that reaction go longer at a cooler temperature. Right? Reactions tend to go cleaner if you do them at a cool temperature. And again, that's always going to be relevant, right? So the reaction that we reflux in teaching lab will probably let go of room temperature or research lab. We do it at room temperature in the teaching lab, we probably cool it to 0 or -78 or something in the research lab. All right, so this is a pretty, I mean, this actually is really nice. You have site specificity. How would I put the NO2? Sorry. You want to play poker with me, even with a mask. How would I put an NH2 on a ring, right? I can put a nitro group on, NO2. Maybe you don't know immediately how to do that. Go back and look at chapter 18. Nitric acid, sulfuric acid, NO2 goes on the ring. You could reduce the NO2 to an NH2, a variety of methods, hydrogen gas, lithium aluminum hydride, reagents that will do that. You have the NH2, so the NO2 is going to be a meta director and a strong deactivator. The NH2 will be, under some conditions, an electron donor, depending if it's protonated or not, be an electron donor and an orthopara director. Right, so you can do all the chemistry you need there, and then if you want to get rid of that NH2, you can, or you can, you can do other chemistry with it. All right, so if you look over here, the Sandmeyer chemistry, you're basically just treating the aryl diazonium salt with a nucleophile. It's not a clean, right? We can't do a backside attack on the N2 plus because, right? Backside attack takes us, we'd have to go through the benzene ring. Can't do that. So the copper is in there to kind of mediate some one electron transfer chemistry. I'm not gonna ask you the mechanism for the Sandmeyer reactions. But it's basically a nucleophile replacing N2. N2 is a leaving group. So it makes sense to think that N2 is always going to be a leaving group, but it's, like I said, you can't really get in here sterically. And so and I think you've already done this, but let's put this in water. What's the mechanism to do that reaction?
Always a glare of light right on the molecule.
So first of all, remember on a mechanism you haven't seen, and maybe you've seen this one because you did a lab report. What bonds get made, what bonds get broken? And then you ask yourself, like, why that particular bond? Why that particular position? Yeah. One nitrogen pi bond's broken. What bond gets formed? Yeah, so basically that carbon has got a bond to that nitrogen, right? We're going to make a sigma bond there. We're going to break a pi bond here. Breaking the pi bond is going to be like that, where you're taking 2 electrons, neutralizing the charge on the nitrogen. We're going to lose a hydrogen. There's a hydrogen on this atom, on the orange dotted carbon atom. There is not a hydrogen there, so we're going to lose 1 hydrogen. The nucleophile here is going to be the benzene ring. So this is an electrophilic aromatic substance. We're going to lose an H off of an electron-rich benzene. We're going to have that electron-rich benzene bonded to something that was electron poor. So the intermediate here would be that, right? Make the bond here. End up with a positive charge there. What does that make the OH group? What can you infer from this that the OH group is? What kind of drug? It's an orthoparadirecting, which means it's a donor or a withdrawer. It's a donor. Right, and so then the last step is just going to be H2O. Taking that proton, remaking the benzene ring. This basically takes us. So you guys remember the azo dilab? It was just last week. It's a dilab for one thing. I've written the word dye up there. So it's DYE, you guys should know what that is. Think back to that lab. The stuff in your beaker or in your test tube was brightly colored. You wound up being able to attach it to fabric. It stayed. What do you think? What do you guys think? We went down there and took that fabric, we ran it through a washing machine. Do you think it would stay? If I get any faith in that? Some of them would, right? So what to stain or to dye a fabric and have it stay, what has to happen is the molecule with the color, the dye molecule, has to have some sort of interaction with the fabric. Right? So if you have a cotton fabric that's got lots of OHs on it, you want a dye molecule with hydrogen bonds. Right? So when I run it through the washing machine, 130-degree Fahrenheit water, say, I need that dye to prefer a hydrogen bond to the fabric rather than the water. You can also put in ionic stuff, but generally speaking, you could make the dye, you could have a fabric that's more hydrophobic and a dye that's more hydrophobic. And so that dye is not going to come off into the water. Right? So there are a lot of ways people, and we've gotten a lot better at this. So even, I said earlier, I'm 51. When I was a little boy, like all the time, we would put, like, you did not wash colors with whites. Has anybody been instructed this by a parent or grandparent? Odds are decent. You guys won't teach your kids. Maybe you will, because we're, parents end up being very bossy. But it's way less of a problem today. Like, I put whites and colors together all the time. I'm lazy. But I have decent modern fabrics and colors don't bleed as much as they used to. I mean, it used to be like, even, you didn't even put like different colors together. If I put a pink shirt in with a blue shirt, I know the color wheel escapes me. I would come out with like two shirts that looked the same. Purple? Okay. That did actually happen a lot. And so now it doesn't happen, so that's nice. Okay, so we don't use a whole lot of azo dyes anymore. We do, there are some, but you guys saw that color. It was easy to make. And in fact, the dye industry sort of gave birth to the modern chemical industry. Right? So there wasn't really, if you go back to the early 19th century, there was, the Industrial Revolution was starting to, go, we discovered the power of the wheel. I guess we discovered that before. Like, we were building stuff and processing things, and machines were starting to take people's jobs. And people got upset about that. In the 1850s, a guy discovered a dye called mauvine. He was actually trying to make quinine to treat malaria. So he was not at all trying to make dyes. He was trying to help humanity get over a terrible disease. He would not have made nearly as much money if he had been successful. All right, so he made no progress at synthesizing quinine which wasn't synthesized for like another 140 years. He treated nobody's malaria, but he made this purple compound that he called lavine, and he became fantastically rich. So probably some of you have heard this, right? Purple is a royal color. So going back to ancient times, the Romans especially, like the Romans, for at least part of their history, you were not legally allowed to wear purple unless you were either in the royal family or a senator or extremely rich, right? Like you could be killed because it was the good old days, and that was the only punishment anybody did. So purple, this guy Perkin came up with a purple dye. Cheap, easy to make. And all of a sudden, everybody's wearing purple and paying him not as much as they would have had to pay before, but a lot. And he becomes rich, and everybody's like, "Oh, we got to make." You know how business is, right? One guy makes something, makes a lot of money, everybody's going to do it. So all of a sudden, in England and Germany, we have a race to make better dyes, more color fast dyes, more cheaper dyes to produce. And there was this. Here. That brings us up to the 1930s, this molecule called frontosil. So how many of you have dyed cells and to look at them through a microscope? Anybody done that? Like, in there also there's like gram, isn't that where we get gram positive and gram, like my biology, I start talking about biology and everybody leaves. This proves that biology is not very interesting. So this was known by the 1930s. Like humans discovered dye molecules in the 1850s. Over the next 70 or 80 years, we build up a huge dye making infrastructure. There's a lot of snake oil salesmen in this time, like the miracle of chemistry. And so, but we still don't have much in the way of medicine. But we knew that some dyes stain certain bacterial cell walls. Like you can use dyes, interestingly, in microbiology. And so this guy, George Domek, is a German, and he knows about this molecule which stains cells. Anyway, before I finish this story, think about the synthesis up here, how we made the mechanism I just went through. Which of these molecules, which side? All right, so there's one aromatic ring and another aromatic ring. The azo dyes are all going to have that structure. A benzene, nitrogen-nitrogen double bond, and another benzene. One of those benzenes will be the nucleophile right up here. Phenol is the nucleophile. One of the benzenes will be the aryl diazonium sulfate. Down here, which one? Take 30 to 45 seconds to figure out which aromatic ring would be the nucleophile, which aromatic ring would be the electric one. One's the nucleophile, one's the electrophile. I can't remember which one. Come up with it, write down your answer and judge yourself. I'll take you through here in a second. All right, so the way to work this out, again, let's go back to the first example I did. So as you think about molecules, examine this fragment. We do this a lot in organic chemistry. We take fragments of the molecule. This is really in large measure how modern medicinal chemistry works. Like this part of the molecule is going to hydrogen bond to that thing. This part of the molecule is going to hit the active site. This part of the molecule is going to hang out into water. This part of the molecule will just be hydrophobic and interact with something else hydrophobic over here. So as you look at this, which of these two benzenes is more electron rich? Yeah, the one with the OH on it. So if you just ignore this, the ring that's more electron rich is a lot more likely to be the nucleophile. And then that would mean this other one, and like this benzene by itself, just a plain old benzene is right. That's the standard. That's neither electron rich or poor, sort of the one in the middle. But sometimes, like this one might be electron poor, and it couldn't even be the nucleophile. So if you look at pronosyl, which I'm sure the Germans pronounce different than that Oklahoma drawl, right? Which ring is more electron rich? Right. This one is NH2. The NH2s have lone pairs on them. Right, so there's two NH2s there. That's a lot of electrons being pumped into that benzene. On the other hand, this sulfur, so sulfur, if it's got a lone pair, would be an electron donor. This sulfur, in large measure, the two SO double bonds. So the SO double bond, way more than the CO double bond, exists as a single bond, lone pair, and the lone pair on oxygen and a positive on the sulfur. So that sulfur, this sulfur bonded to the ring with two oxygens on it is a really strong electron withdrawal. So this one's electron poor. This one is electron rich. So if I said, hey, you got to synthesize pronosyl, you would want to take the electron rich ring. And so that means, what that also means is, this is the bond that got made, right? So we make the carbon nitrogen bond from the electron rich benzene, and it attaches to the outside nitrogen, the one that came from the nitrite on the other benzene. This one had to come from aniline. So this one had to come from just NH2. So we take aniline, treat it with mono, then dump in phenol. I think you guys, I don't know if we actually did we make that one? Anybody remember if we actually made that one? I know there was a phenol. I don't remember if we used just aniline. Down here, we would take 1,3-diaminobenzene, and we would use the aniline with the sulfur, the sulfonamide group on it. That nitrogen would come from home.
Why would the nitrogen bond there? Why would it bond? Oh, I guess that's what okay.
Right. So as you think about this, right, this would have been, sorry, this would have been a nitrogen-nitrogen triple bond. This ring attacks it. These two groups are electron rich or electron donors. So they're ortho para directors. We're ortho to one, we're para to the other.
And then for
this one, it doesn't matter. We don't actually make that bond. Is that what you're going to ask?
But when you make the reagent, you would have to add the sulfur after you add it, right? That would be
not necessarily. Right. Yeah, but we don't make it that way. So the compound. So anyway, let me write this out. I'm gonna go right to left, which sometimes. I was going to tell you it sometimes messes you up. It also sometimes messes me up. So the reaction to make pronosyl would be this. Now we'll get out of the way in a minute. So the reaction, this is badly drawn. We would start with this animal, right? We start with this nitrogen on the ring. If I ask you, start with benzene, maybe you guys have looked at your synthesis assignment that came out. Like all the carbons in the molecule I emailed to you yesterday have benzene or ethanol. So if I had you do this, like you'd have to add the sulfur, you'd have to add this, you'd have to add this group in, you'd have to add that group in, you'd have to add those groups in. It's a long synthesis. Nope, nobody got this molecule. Okay, so but if I just say what reaction, like if this was a question, like how would you make Prontosil using, how would you make Prontosil with an azo disynthesis? You're allowed to start with that. You just need this molecule. We're going to treat with sodium nitrite and HCl. That will get us to the diazo compound. Then we dump in our electron-rich nucleophile. And we put base in. You guys might remember you added base. And really the reason you're adding base is to neutralize. You want to neutralize the HCl. And then that last step, you need to take this hydrogen off. So that's nice to have there. And you really don't want, right? These NH2s are basic. So if you have strong acid, the NH2s are protonated. And then that benzene's not going to be nucleophilic. Okay, so if you get asked a question like that, I don't know who would ask you that such a thing. But if you do, you take your azo di, one ring is going to be electron rich, one ring might be electron 4. If you have 2 electron rich rings, you could go either way. If you have 2 electron 4 rings, you have to do something after you make the azo di to make them electron 4, right? There has to be one of those rings that's electron rich to be a nucleophile. So here with Prontosil, we identify this ring as electron rich. That's going to be the nucleophile. That means this had to be a nitrogen-nitrogen triple bond. We make that bond, which means then we start with that nitrogen as an example. All right, I started in this whole thing about dyes and Germans. And so this guy, Prontosil had been around for a while. His company made Prontosil, sold it as a dye, both to microbiologists, who were just biologists at that time, and to, clothing manufacturers. Like they made more money selling it to the industry. So this is like 1934, 1935. So Hitler's been in power a couple of years. Domek's daughter gets, has an infection. And this is something like, how many of you, before you came to Wake Forest, how many of you took an antibiotic? Like basically everybody, right? Have you ever taken an antibiotic? I'm not trying to HIPAA anybody here, but my assumption is, man, if you haven't taken an antibiotic, you're superhuman. That's just sort of routine now. Before we had antibiotics, people died at a very young age. If you look at, mortality, human mortality, we live longer now. That's a weird statistical number. If you look at the very oldest people that died 400 years ago, they died about the same age people die now. Just way fewer of them got to 90. Some of that, how did you get to 90? Well, some's luck, some is having money, same as now. Some is just never getting hurt. If you work on a factory floor that's dirty, if you work on a farm. So we talked the other day about how do we fertilize things? Well, we just spread shit everywhere. So that's your job. I spread manure all over this field. Oh, and I just cut myself with something in the manure. All right. You do that when you're 19 and, it gets infected and there's nothing you can do about it. And you die at 19. So that didn't happen now. So 2 things happen, right? We recognize that cutting yourself with manure on it's a bad idea. Don't do that. And if you do, we have drugs to treat. So anyway, this guy Domek's daughter gets some sort of infection. She's sick. She's got a fever. We all sort of recognize what an infection looks like. And basically the doctor's like, yeah, she's going to die. She's 7 or 8. And that's just that's what happened. And he's desperate. And he knows that this dye will stain bacteria. And so they know we know by this point, the thing causing the fever and the illness is a bacterium. hey, I've got this compound that stains bacteria. Like maybe if I put that in there, I don't know, it'll stain the bacteria and they'll die or something. He gives her Pontosil, and like a day later, she's fine. Okay, so if you've had antibiotics for a real bacterial infection, like very often it's night and day, right? Like sometimes we get antibiotics and we're just kind of guessing. We think it's bacterial, but it's not. Or it might be, today we have to worry about a bacterial infection being, the bacteria being resistant to the antibiotic. Pump some Prontosil into this girl and she is fine. And this, like people have been looking for this. People have been thinking it ought to be possible. It turns out Prontosil doesn't do anything. Well, that's not true. Prontosil itself, this molecule, does not kill bacteria. All right, so what happens is, so in the body, Prontosil is broken down. That that nitrogen double bond that we went to all this trouble to make is cleaved. And what we get the aniline that we started with. Okay, that's the thing that kills the bacteria. But here's the, cool, weird thing. If we just administer this, right? So, I mean, we're just feeding this girl like pellets of dye. If we feed her pellets of this compound, she does not get better. Sulfa drugs, yeah. So turns out this is the group, and I forget exactly what the chemistry is. The cool thing about these sulfurs is that's a really electrophilic group. You guys remember when we did chapter 19, chapter 20, nucleophiles that add to a carbonyl to get a tetrahedral intermediate? There are a lot of enzymes that catalyze the conversion of one carbonyl compound to another carbonyl compound, like when we make proteins. The tetrahedral intermediate looks like this. And so these sulfur, you can also do this with phosphorus. They look like that tetrahedral intermediate, and so they'll bind to the enzyme that catalyzes that reaction better than the substrates. And so this compound doesn't make a covalent bond, but it makes non-covalent bonds to an enzyme active site and just kind of sits there, knocks out that enzyme, and the bacteria dies. All right. The reason we can't just administer this is it doesn't get into cells. So making drugs is really hard. I don't mean that recreationally. Making drugs, making meth, you guys all have plenty of chemistry experience and brain power to make meth. I mean, I'm just saying you do. Like if the cops come ask me, could this person make meth? Yeah, sure. But I mean, I'm not trying to praise you. That's going to be my answer to almost anyone. Like it's not hard. It's cooking. It's literally called cooking. Like you just mix stuff together. All right. Making drugs, making medicinally useful drugs is very tricky, right? We know that meth does certain things. You don't have to figure that out. But if you don't know what happens, like if you're trying to come up with a drug that's got a new effect, it's really hard to work that out. Right? So the way we typically do this is we take a cell, well, actually, we might even take a protein. Like I know this enzyme is involved in this disease. So the first step is let's make a molecule that inhibits the enzyme. Hooray, you did that. I've actually myself done this 4 or 5 times. You'll note that I'm not a billionaire. Killing or inhibiting an enzyme in a test tube is pretty easy. Even killing a cell is pretty easy. But what you have to do with a drug is it has to go into a living organism, like a human, that's extremely complicated. It has to go everywhere, right? Like if I eat something, it gets absorbed into my system and it sort of goes everywhere. So it's got to go to the right place. It's got to do the thing it does in the test tube in that place. It's got to get into a cell, right? So you guys will or have taken biology classes where you learn what the cell wall is like. If, you know, if you're really polar and you hydrogen bond really well, or God forbid you're ionic, like there's no way into the cell. Right, so basically prontosil is a little more hydrophobic, not a lot, than this precursor molecule. And it can slip through the cell a little easier. Still not perfect. And so sulfa drugs, right? The next 10 years after this discovery, everybody is trying to make versions of this, versions of prontosil. Going to add this, you know, I'll add a methyl. No, then I'll add an ethyl. Then I'll add a propyl and an isopropyl and a T-butyl and a benzyl and a phenyl. And that's what medicinal chemists do. It's like, I'm going to make 100 versions of this compound with all these different side chains and see which one works best. But until you actually put the drug into a human and it does the thing you want it to do without doing a whole bunch of stuff you don't want it to do, you don't know that you have a drug. So anybody who's taken antibiotics, has anybody ever had like side effects to that? Anybody in here? Right, yeah, that is HIPAA stuff. Like you can be allergic to penicillin and just die. That was a shock to him. Hey, a miracle drug. Oh, it kills some people. There's always going to be a drawback to that. All right, so we have a med chem class here. Probably you're only going to take it if you're a chem major. But you can take it, there's a medicinal chemistry major, like a line of chemistry major that's medicinal chemistry, and then you can take that as an elective if you're a chem. So it's a really good class if you're like, again, I don't think it's going to help you get into med school, but as a doctor, it's something you'll need to know, and you'll see a lot of that in the first couple of years. We call this a prodrug, not because of prontosil. It's an accident, and it's English only that works. The first three letters are the same there. A prodrug is a compound that is inactive, but that when it's administered to a patient, the patient's body somehow activates it. It can cleave bonds, it can add bonds, it can make a conjugate that then becomes active. And this is a very common strategy. And for a lot of so when we try to make an anti-cancer drug, a lot of that is trying to make a compound that will be activated only in a tumor cell, right? So what is the chemistry of a tumor cell? They tend to have a little lower pH. They tend to have some enzymes that other cells don't, right? What the definition of a cancer cell, they grow really fast. So anything involved in cell growth, if you can come up with a compound that's super toxic, but only gets activated in a tumor cell, you can kill cancer. Like again, it's not hard to kill a cancer cell. Bleach does it. This is a famous joke, right? Like, why don't I kill the coronavirus by drinking bleach? That will work. What else does it do? It kills you. Like again, killing a cell, easy. Killing a cell in the middle of a bunch of other cells without killing those other cells is hard. And all does come to this. Plus, it's the 1930s in Nazi Germany, right? Like, this was true, I shouldn't say Nazi Germany. It was true in the US, it was true in England, it was true everywhere in the world. There really weren't laws on the books about when can you trial a drug on your daughter. The answer was any time you like. And like I said, we found a lot of cool drugs this way. We also killed a lot of people and hurt a lot of people. So now there are very strict rules on this. If you guys do make any drugs at home, don't give them to humans. Test them in test tubes and rats. Any questions about any of this stuff? Okay, I'm going to switch gears sort of wildly. So this was the bonus. I don't always do the bonus in class, but we want to do this time because I wanted to introduce a type of addition that I didn't talk about in class. In chapter 21. So this sort of will finish off 21. We're done with 22. So if you look at this, and again, think about this in terms of, I asked for the mechanism for this process. It's clearly not one step. We're going to make a sulfur carbon bond. We're going to make a carbon carbon bond. And then we're going to protonate an OH. We're going to lose the carbon carbon pi bond. All right, so a lot of people got all of those parts, but didn't put them in the right order. So the reaction is the first step is for the SCH3 to add to the double bond, the carbon-carbon double bond. So why can this happen? Right, if you think about resonance structures, you can always just pop the pi electrons up onto the carbonyl. Right, you're used to seeing that resonance structure. So nucleophiles can attack the carbon of the carbonyl. This is just now an allylic cation. We can move these pi electrons there. And what we find is for this double bond being bonded to that carbonyl, the carbon-carbon double bond takes on some of the property of the carbon-oxygen double bond. Right, basically putting a strong electron withdrawing group on the double bond on the alkene polarizes the alkene. So now we can have a nucleophile intact. Here, this is called a 1,4 addition. It's called a conjugate addition, sometimes called a Michael addition. You'll see that in chapter 21. And that the result is an enolate. From there, that then, like if I gave you this enolate and I said there was benzaldehyde in there, I think at this point you guys would know what happens next. Right? The enolate attacks the carbonyl. O minus pH. And then we're going to take a proton from the ethanol and get up there. All right. So here's the thing. Why doesn't that sulfur add to the carbonyl itself? Which we would call a 1,2 addition. So I've shown, and your answer could be a perfectly simple one, right? Like, why did the several people who answered this question correctly, why did they have the sulfur attack that carbon? The reason is, well, that's where the sulfur is. Right? So if I give you the product, you don't have to come up with why does that happen? You just know that happened. But how might you predict that? Right? Why would this sulfur not attack the carbonyl? Why would it attack the alkene carbon? Anybody think of a reason? Sorry, do you want to? Is it electron pressure? It's not that. The answer is, I was asking it as a trick question. So the sulfur does attack the carbon. You know, why doesn't it attack the carbonyl? Well, it does. So if you have we have this situation. Right, so the nucleophile can attack the carbonyl, or it can attack the beta carbon of the alkene. If it attacks the carbonyl, we call this a 1,2. If it attacks the beta, it's a 1,4. It always attacks the carbonyl first. So anytime a nucleophile has a choice to attack the carbonyl carbon or the alkene carbon, it's going to attack the carbonyl carbon first. Right? If you take this ketone, right? If we take this alpha beta unsaturated ketone, right? The alpha carbon is here, that's a beta carbon. Alpha beta unsaturated, there's an alkene there. If I treat that alpha beta unsaturated ketone with phenyl Grignard, phenyl adds into the ketone, that's what I get. If I treat that same ketone with methoxide, methoxide ends up on the beta carbon. So here's what I want you to do. I want you to draw what happens if the methoxide attacks the carbonyl. This will be the last thing we do. What happens if the methoxide attacks the carbonyl carbon? Get that, right? What is that going to do? Let me knock it back off. It will knock it back off. Should be the same as if we had. We can make this intermediate the same way. Right? If I take this ester and I add methyl Grignard to it, I get here. Grignards always add the ketones twice, right? I didn't say that right. Sorry. Don't. Grignards always add the esters twice, not ketones. So at this point, O minus just kicks the methoxide back out, go back up there, and eventually we're going to make the stronger bond. It turns out this is, you just sort of have to know this empirically, that methoxide bonding to the beta carbon makes a stronger bond than bonding to the carbonyl. So this is a classic kinetic thermodynamic product. Thermodynamic product is always 1,4 addition, beta addition. The kinetic product is 1,2 addition. So if, same thing then, if the 1,2 addition product is reversible, it reverses and you end up with the thermodynamic product. If I add a Grignard, right, the 1,2 product is not reversible. That Grignard goes in, can't come back out. So if you have a nucleophile that adds to the carbonyl and can't be kicked out, you'll get 1,2 addition. If you have a nucleophile that adds to the carbonyl and can be kicked out, it gets kicked out. I have gone 2 minutes over. I apologize if you need to fly for the bus. I've got some office hours posted tomorrow. We have one class left before Thanksgiving. Sorry, that was a tempting, that sounded better than it was. We have one class left before Thanksgiving. Look at the polymer chapter a little bit before Monday, and we'll talk about polymers. I don't know. I'll send that to you. It's like 27, 26, 27, 28. I'll see some of you in lab in a minute.